Hello, guys. So this will be a small lecture. Okay, I will just give you an example in which we combine both DC and AC analysis. Okay, so let's first recap what we have taken so far. So let's see what here a recap. So we take two circuits in common emitter so far. So we take a circuit like this. With no RE resistance. And we take also another approach in which we put what's called degenerate resistance in the emitter. So it is basically the same circuit, exactly the same, but we'll just add a resistance in the emitter here. So the emitter is not connected directly to the ground, it's connected through a resistance to the ground. This resistance is called RE or degenerate resistance. Okay? And why we put this resistance? Because to make the emitter amplifier immune to the temperature changes or beta changes. Okay, so you will have a stable operation. If you have two rooms, one warm room and another cold room, and the same amplifier, the amplification here will be exactly the same as the amplification in the other room. Okay, we said that for the first amplifier here, Ri is equal to RB capital parallel to RB, I'm sorry. RO is equal to RC, and EV is equal to minus GM RC parallel RL. Here, Ri changed, it became R by parallel to RB parallel to R by plus beta plus 1 RE. It's higher, which is good. But RO is still the same. EV reduces, it became minus GM RC parallel RL over 1 plus GM RE, but it become more immune to beta changes or GM changes. If you look at this equation here, GM in the numerator and the denominator. So a change in the numerator will be a little bit cancelled by a change in the denominator. So AV will be stable, a little bit stable, more stable. Okay? In both two examples, we just concentrated on the AC analysis. We didn't touch the DC analysis. We take it as numbers. If IC is equal whatever, RC is equal whatever, just to calculate the parameters that we get from the AC circuit. In this lecture, I'm gonna give you an example in which we consider, a circuit, and we're gonna solve it from scratch. We solve the DC analysis or the DC portion of it, and also the AC portion of it. It should be quite simple. Okay. At the same time, we're gonna check another type of biasing. So here we are biasing or making the point, giving the 0.7 to the base emitter junction through this resistance RB. We're gonna do something similar, but using the voltage divider. So let's do that together now. So here is an example. We have, let me draw this circuit in another color here. So we have resistor R, So voltage divider now. 15 here. RC, RE, R2, R1. Then we have a resistor and a capacitor and R signal and V signal. Here is also the. Then we have here CB, CC, R load, and we have here a capacitor, CE. This is another approach. So we're gonna use only RE in the DC. Okay, because remember, the capacitor in AC will be shorted. So this will short out RE because it's in parallel with it. So the combination will be zero. So it's not there in the AC, as we will see later. I'm just after 10 minutes or something. Okay. So here we are, RE will be, I'm sorry, our input will be the same as the previous normal common emitter circuit. AV will be high, okay, although it's still a little bit stable, more stable, because we're gonna make the stability in DC, okay, as we will see now, okay. So let us solve it. So what is the requirement? First, find IC and our input, our output, EV node, open circuit voltage gain, AV, and GV. All these are requirements. Good. What are the numbers? So we have R2 is equal to 15 kilo ohms. R1 is 27 kilo ohms. RC is equal to 3.9 kilo ohms. RE is 2.4 kilo ohms. RL is 2, oops, very sorry. Okay, that's fine. Good. RE is 2.4 kilo ohms. RA is 2 kilo ohms. R signal 2 kilo ohms. And beta is 100. Okay, this is 15. We check the numbers, yes. Okay, so let us solve this. First, we start by the DC analysis. In DC analysis, first cancel all EC sources, which is V signal, just one source, only V signal. Number two, so make short here. Number two, all capacitors are open. Replace any capacitor with open circuit. So let's do that. So if this is open circuit, RL will be, it's not connected. If this is open circuit, it's also can be considered as not connected. If this is open, then this part is not connected. So basically, you will have this circuit, which is exactly the same circuit that we used to solve, all over again in the last few lectures. RC, RE, R2, R1. Okay. This is after canceling all EC sources and marking any capacitor as open circuit. Okay. Basically, we remove any EC stuff. Then let's solve the circuit. Okay. So basically, we're gonna get the Thevenin equivalent of this guy. We can replace this portion of the circuit with Thevenin. So the circuit will be something like this. RE, RC, 15. Yeah, just you don't need to extend it. 15. Then this part R1 and R2 will be R7 and V7. V7 is equal to, if you just review the few previous lectures, we did this before many times. So V7 is actually 15 multiplied by R2 over R1 plus R2. If we substitute, this is 5.357. Okay, R7 is equal to R1 parallel R2. So this will be 9.642 kilo ohms. This is volt. Good. Now we can solve and get IB, which is here. So IB, also review the previous lecture. It's easy. V7 from this loop here, the internal loop, minus 0.7. Here is the 0.7 over R7 plus beta plus 1 RE. I'll keep it in that way, although I will put just the number for it, 0.01847 milliamperes. IC is equal to beta IB, so beta multiplied by same stuff, V7 minus 0.7 over R7 plus beta plus 1 RE. One thing here, why we put RE? So if RE is 0, then IC will be beta multiplied by V7 minus 0.7 over R7, and that's it, right? So any change in beta, in that case, if there is no RE, if RE is 0, this will affect, this will change IC too much, okay, because it's direct proportionality. But now there is beta in the numerator and another beta in the denominator. Remember, beta is plus 1 is approximately equal to beta. So a change here will be cancelled by a change in the denominator. Okay, so that circuit is more stable. And when we put the capacitor, this will cancel the effect of RE in the AC portion. So the gain will be high still. Okay, it's a trade-off. Good. So this will be just multiply this number by 100, so 1847 milliamperes. Of course, now we can determine GM. GM is equal to IC over VT. Okay, so if we calculate GM, it will be 73.88 milliohm minus 1. And remember now GM is more stable or more stable, yeah. So it will not affect much if it will not change much if beta changes. We can also determine R pi. R pi is equal, R pi is coming from IB. R pi is equal to VT over IB. It would be equal to 1,353 kilo ohms. Okay, that's all for the DC. We can do another step to check if we really working in the active region, because it's amplifier. We should be in the active region. So we can do that as well. So we can determine VC. VC is equal to VCC minus ICRC. We know all of that. So this will be 7.796 volt. We can determine VB. VB is equal to V7 minus IB R7. This is the voltage at that point, equal to V7 minus the voltage drop across R7. So this will be equal to 5,178 volt as well. And VBC is equal to, when you subtract these from each other, this will be minus 2.6. Well, of course, this is less than 0.4, so we are really in the active region, and we should be happy. One little note before also we go to the AC analysis. Let's check VC. VC is equal to 7.796. Remember in our first lecture on amplification, we said that one of the best values to design the circuit is to work at the middle of the active region, which approximately VCC over 2. VCC here is, let's write this with green. VCC over 2 is 15 over 2, it is 7.5. So this is actually near the middle of the active region, which is good. Okay. Just when you are making sense of the numbers. Good. That's all for the DC analysis. We get GM, we get RBI. We check that we are really working in active region. That's all. Now we go to the AC analysis. So in the AC analysis, number 2, go back to blue. The AC analysis. What we're going to do in the AC analysis? From AC analysis, we should find RI, RO, EV node, EV, GV. Okay, what we should do to do that? We should drive first the AC circuit of the original circuit. And to do that, there are steps also. Number 1, cancel DC sources, which is VCC in that case. For some other problems that we will see in the future, you might have a current source, open circuit. But for this guy, it will be short circuit because it's a voltage source. Number 2, replace capacitors with short circuits. So let's do that very quick. So let's draw the circuit. And you can use let's use the original circuit. That's fine. You can use the Thevenin equivalent as well, but that's fine. Let's draw the original circuit. Good. So let's apply this. So we're gonna short first VCC. So this will be just a ground. So let's just remove all such stuff. I draw it intentionally just to show you the exact steps. So here will be a ground. This is called AC ground, by the way, because it's a virtual ground, just created as a model, or in the model. Then we shorted all the capacitors. So short this and this. Okay, let's remove that guy now. Yeah, let's put with green. So we know that it was a capacitor in before. Also remove that guy and make it in green as in red as well. And now when we short this guy as well, so this resistance RE will have in parallel a short circuit. So the parallel combination of a short and a resistance just as the short. So this will cancel RE. So we can just replace all that by a simple short, a simple wire, like this. So this CE capacitor has canceled the effect of RE in AC. So EV should be high as well, as we expect from common emitter circuits. But of course, our input will be the same. The third step is to replace the transistor by its AC equivalent circuit. So replace the transistor with the AC small signal model, circuit model. So let's do that very quick. So we have, so let's go down. We have beta IB or GMV by the way. I always use beta IB just, for some historical reason, but you can use GMV by. Okay, it's up to you. That's fine. It is IB. It is I by. Okay. And here is the emitter. Here is the base. Here is the collector. And here is IC, by the way. AC, IC is just bit IB. Then we connect the rest of the circuit. First, the emitter is connected to ground. Very nice. So that's finished. So let's mark that's finished. Now let's go to the base. Base, we have many branches out of the base. We have this to ground, R1, finished. We have this to ground, R2, I mean. And we have this guy to ground. So this R signal and V signal. So R signal and V signal. Good. Now we go to the collector, the last thing. I have only two branches. One is this is RL, guys. RL to ground and RC to ground. I prefer always to draw RC first. Then at the end, RL. And before anything, put the directions of our input, our output, and V input. Okay, so V input is here. Here is RI. And VO is here. And here is RO. Good. So let's take this to another slide and start solving or determining, all the required values, our input, our output, AV, and AI. So let's copy this. Let's go to another slide, put it down. Good. Good. Okay, so now just one correction here. This is RO. Let's solve now. Let's start by RI. Number one, RI. Okay. So for RI, it is the resistance seen by the input source. Okay. So between these two terminals. So I will draw everything in the circuit except R signal and V signal. And we're gonna, imagine that there is imaginary source here, Vx, Ix, Ix, and Vx. Okay. It is R2, R1, R by, beta IB, RC, RL. Okay. So basically, it is, IB. It's basically R1 parallel R2 parallel R by. It's very clear because again, this circuit is coupled or isolated from this circuit. They are two circuits, although they have dependency because of the current source, but this is in the second circuit, not in the first circuit. So we can safely say it's R1 parallel R2 parallel R1. Okay? So here R1 parallel R2 parallel R by. If you want to go deep, that's fine. Let's do it. So we can say also it's Vx over Ix. What is Vx? Vx is the voltage across R2 or R1 or R by. They are all parallel. They have the same voltage. Okay. So Vx is actually IB multiplied by R by. How about Ix? So IB equal to Ix multiplied by. So we have here three resistances in parallel. Okay. So it's equal to the further resistance. If you just review the circuit theory, this is easy. It should be Ix multiplied by the further resistance R1 parallel R2 over R by plus R1 parallel R2. Okay, so this will be equal to IB R by, then in here Ix is IB R by plus R1 parallel R2, and this will go in here. Okay, so this will be go this. So this is RB R by R1 parallel R2 over R by plus R1 parallel R2. And what is this? This is actually R by parallel R1 parallel R2. Okay, that's it. Again, it's very clear without Vx or Ix or whatever. Now RO. So for RO, we look after the source. So after the from this location. So just not to mess up. So we not draw our load. Instead, we draw just imaginary source. Vx that giving Ix. Then we draw the rest of the circuit, RC, beta IB, and we cancel any other source, any other independent source. So in that case, we will cancel V signal. Of course, everything here is connected to ground, so we can connect them. So R1, R2, here is our signal. Here is IB. RO is Vx over Ix. But we need to know what is IB exactly. Okay. So if we look at this circuit, for example, this loop here, if we can, you know, yeah, we can do that in that way. So RC beta IB, and this can be in that way. R by, and these resistances are in parallel. So just to draw one of them as one, a combination. Here is R1 parallel R2 parallel R signal. And here is IB. Okay. And here is VXIX. From this loop here, okay, IB R by plus IB R1 parallel R2 parallel R signal equal to 0. So IB R by plus R1 parallel R2 parallel R signal equal to 0. So either IB is equal to 0 or R by plus R1 parallel R2 parallel R signal equal to 0. Of course, these are constants. They are not 0. The only thing that can be 0 is IB. So IB in that case is 0 when we cancel our V signal, the input source, because it was actually the source of IB. So IB is equal to 0. So the dependent source beta IB is actually equal to 0. So it's open circuit. So we can just draw Vx, and here is Ix, and only RC like this. So basically this is equal to RC. Good. Number 3. EV naught, which is actually equal to VO over VI when RL is considered infinity. Open or not connected, open circuit loop gain, voltage gain, I'm sorry. Okay, so let me copy and paste. I think we already have it, so we just paste it very quick here. Yeah, we have it already. Okay, so VO is equal to, remember now we don't have RE, so let me just omit it. Yeah. So VO is equal to, now without RE, without our load, beta IB or IC will also flow in RC. So this current will flow in that way. So, but it will make a voltage drop in opposite to VO. So VO is equal to minus beta IB RC. How about VO, V input? V input between these two terminals. It is the voltage of R2 or R1 or R by, because all three resistances are in parallel. So whatever you know the current in each one, use it. We know the current in R by. So it's IB R by. So AV naught equal to VO minus beta IB RC VI IB R by. IB goes with IB. Remember, we should always omit IB or V by if you are using GMV by. So this will give you minus RC over R by over beta, which is 1 over GM. So this one minus GM RC. Exactly the same as the first one, very first one that we solved with no RE. Number 3. I'm sorry, 4. AV. AV is just VO over the regular one over V input with RL there. So let us put the circuit again. Yeah. So here VO Now beta IB is flowing in the parallel combination of RL and RC. So minus beta IB RL parallel RC. So VO is the voltage between these two nodes, this node and the ground. We know for the parallel combination, the total current flows in this is IC or beta IB, the flowing from bottom to up. So the voltage drop is positive, negative, opposite to VO. So VO is equal to minus beta IB RL parallel RC. And V input will not change. Again, it's the input voltage on R2 or R1 or R pi. For anyone, if you know the current in anyone, just use it. We know the current in R pi is equal to IB. So IB multiplied by R pi. So EV equal to minus beta IB RL parallel RC over IB R pi. IB will goes away. And again, beta over R pi is GM. So this is minus GM RC parallel RL. Okay. Just before we forget, we should also determine all the, yeah, we should do that. We should determine all the combination. So here we have the numbers because it's an example problem. So we have the numbers. So let's do that very quick. Yeah. So if you do that, this will be 101.865 kilo ohms. We know R1, we know R2, and we know R pi. So we can determine this. RC, of course, is simple, 3.9 kilo ohms. And for EV naught, it is, I didn't do that, but I did for AV. So AV is equal to minus 97.671. Okay. You can guess. No, we can't because RL is different from R. Okay. So you guys do AV naught minus GM RC. Okay, the final requirement is the overall voltage gain. JV. It's equal to VO again over V signal. And if you multiply and divide by V input, I'm sorry, you can write it in that way, VO over V signal, I'm sorry, over V input, multiplied by V input over V signal. Good. So let us do again, put again the circuit. This can be reduced to the following shape. Since we know already our input, so we can remove all of that and put our input instead. Here is our signal, here is V signal. And remember, here is VI. So from this, VI is equal to V signal. It's a voltage divider. V signal, our input, or RI. We always use RI. So let's stick to RI, not RN, although I mean the same. RI over RI plus R signal. Okay. So from this, VI over V signal is actually equal to RI divided by RI plus R signal. So VO over VI is actually EV. We know it. We just calculated it's minus 97.7. And this guy is actually this guy, Ri over Ri plus R signal. So if we, substitute it for AV and we know Ri, it's 1 point something kilo ohms, and we know our signal, it's around 2 kilo ohms. So this will be minus 36.368, and it's dimensionless, it's not volt or it's dimensionless. Okay, so this is an example, okay, in which we did both words. We did the DC analysis and the AC analysis. Okay, we did use, or a circuit that we only use in DC. We did use another circuit in which we use it only for AC. Okay, and determined our input, our output, EV naught, EV, and GV as well. Okay, hope you guys this will help you. I will soon make a kind of homework for you, a series of questions. Okay, and I hope you solve it using the techniques that we learned in this 3 lectures in one day. Okay, thank you very much and have a great day. Bye bye.